Thank you. My name is Fred Rank. I'm a safety engineer with FHWA's Resource Center, Safety and Design Team. Today's webinar is on HSM applications to suburban urban streets. And this is probably one of the most wonderful and rich and helpful and instructive portions of the entire Highway Safety Manual. Answers in terms of being able to quantify safety for suburban urban streets have eluded most of us in the professional transportation discipline for a long, long time. The Highway Safety Manual in Chapter 12, which we're going to cover for the segment portion of Chapter 12 today, is rich, has very robust analysis tools, and should prove quite helpful to you in your work in dealing with urban suburban streets. In getting started this morning, I'd like to call your attention to the poll in the upper right. And if you'd be so kind to help us in conducting these webinars, we'd greatly appreciate it by you indicating and clicking on how many people are in the room with you on your call-in line today. We, of course, can tell how many lines are and how many attendees are from the attendee list, but it's always kind of elusive, and it helps us to know just how many people are actually participating in the webinar. Also on the right-hand side today, you'll see a HSM webinar series presentation file share pod. That has in it the individual files for each of the sessions that we have presented to you in the entire webinar series, and you can download those after today's webinar has completed. We are going to present the material today to you in 3 sessions: an introduction, the crash prediction models for urban suburban streets, and also a 3rd session on the appropriate crash modification factors. With that, we'll get started, and I'll move to the presentation room. I see that Kansas DOT has raised their hand. We will take questions at the end. If you have something that you're experiencing difficulty with on today's webinar, please let us know in the chat pod. I'm now going to toggle the full screen to enable you to be able to see the full screen for the presentations we'll be making today. This is the 7th in a series of webinars. There will actually be 13 of them conducted in this series running through July. We've covered already the overview, 2-lane highways, 2-lane highway intersections, urban suburban intersections, project ID, rural multi-lane highways, and today's webinar is on urban suburban streets. The 7th in the series. Session 1 will be done by George Merritt, safety engineer out of our Atlanta office of the Safety and Design Team. And with this, I turn it over to George for Session 1.
Thanks, Fred. Good morning, everybody. Again, my name is George Merritt, and I'd like to welcome all of you to today's webinar on the Highway Safety Manual. And we're going to be focusing on suburban urban multi-lane streets. There will be 3 sessions today. The first session is sort of an introduction to some fairly sophisticated tools that can help you when dealing with projects on suburban and urban multi-lane streets. So welcome, and with this we'll begin. Again, my name is George Merritt. And also on the line that will be coming up later will be Gene Amperano and Fred Rank, who you've already heard from. All 3 of us work for Federal Highway Administration. We are in the Resource Center, and we serve on the Safety and Design Technical Services team. You will find in this introductory session that basically we're going to talk about some safety performance or the safety performance of suburban and urban streets. And as well, we're also going to define the substantive safety as opposed to nominal safety and describe the differences between the 2. But first, let's start by looking at some statistics and getting a little bit of a handle on some perspective related to safety. If we take the entire road network in the United States, we're looking at about 4 million miles of roadways. And then if we further break that down and look at the U.S. federal aid system, it's approximately 1 million miles of roadways. When looking at multi-lane facilities on the 17% of our federal aid system, and then that's further divided into multi-lane undivided and multi-lane divided highways. So even though we have a small percentage of these roads, we have a lot of issues. And I would be remiss not to introduce or to share with you crash statistics on intersections, because they're pretty astounding. This is a 2008 table, or data is from 2008, and essentially looking at all crashes on our roadways. About 50-some-odd% of our crashes are occurring at intersections. And if we combine both injury crashes and fatal crashes, we're seeing over half of that statistic happening at intersections. Now, if we intersection crashes, and you know, the majority of our crashes that are causing fatalities are related to roadway departure crashes and horizontal curves. But nonetheless, we are still seeing a lot of crashes in our intersections. And today's webinar is not necessarily going to discuss intersections, but I don't want to sidetrack that. We are going to be talking about the roadway segment portions of urban and suburban multi-lane roads. Now, some of the key safety principles and relationships in terms of highway designers, how we design projects, and some of the things that we've been doing in the past. We have always used knowledge and judgment in the design decision-making process. We have tried to design all of our projects, or most of our projects, to at least meet the minimum standards that we adhere to. And for even and avoid design exceptions, if you will. And a lot of times we have to exercise judgment, and a lot of how we evaluate our project design is based on the actual standards that we have to compare to. However, there's a lot of these decisions that we make that, although we may meet standards or those design standards, we may not necessarily make a highway, and I'm going to hold my hands up and put this in quotes, we may not necessarily make that highway safe. I'll explain more what I mean by safe here in a minute. There's also a lot of the decisions that we make that are related to other things than just what we consider to be our standards that we're trying to meet. For example, the spacing between intersections has an effect or an influence on the safety performance, also on the operational performance of our roadway. And there's other examples, and in fact, I'm going to show you an example looking at the center two-way left turn lane that will help reinforce this idea. Although it's not a standard, it certainly has an effect on our project. Now, in terms of standards, we can relate our safety performance, and we have in the past, as if we are complying or meeting the minimum geometric design standards, and we're in compliance with these standards for our project, we have assumed that we are achieving some nominal level of safety performance, or we are achieving some nominal level of safety. However, without further examination, we don't necessarily really understand how that design decision, whether it meets the minimum or exceeds the minimum, how it really has a performance impact on safety. And that's what we call substantive safety. And that's talking about the anticipated crash frequency, or also looking at the historical crash frequency, the observed crash frequency, as well as the crash severity. And we are starting to understand how to relate some of our geometric design decisions to predict how it will affect the crash frequency as well as crash severity. And that's what the Highway Safety Manual provides for us. Now, let me back up for a moment. I also want to mention there should be a picture on the bottom right-hand corner of your screen of the Highway Safety Manual. But AASHTO has fully endorsed the concept of substantive safety as a part of the normal process, and you'll see it in pretty much all of the manuals that AASHTO publishes. Now, nominal safety, let's kind of look at it as the old way of doing things. We have essentially designed our projects to try to meet or exceed the minimum geometric design standards, and those standards are based on research. They're based on experience. They're there to provide some consistency between our roadway networks and systems across the country. And also from a level of quality, we understand that that's a way to achieve a minimum level of quality for our projects. We also consider cost effectiveness when we design our projects, and all of this goes into the decision making, and that's what we used to base our design decisions on. I'm not going to speak too much about tort liability or legal liability. That's for all of you to decide on your own because everybody's a little bit different. But essentially, we design our projects to determine whether or not we comply with those geometric design standards. And then we have an assumption that we're meeting some nominal level of safety. But let me take it a step further, and this is where the Highway Safety Manual is really going to help all of you with our project design decision making. And this is a pretty common example of a 4-lane arterial. Actually, it's a 5-lane arterial, but the project is basically looking at how can we accommodate the traffic in this particular location. And we want to have two 12-foot lanes in each direction, and our traffic is 20,000 ADT. Well, this is a pretty common example of a urban or a suburban arterial, and probably many of you out there can recognize the two-way left turn lane that we may or may not have had an opportunity to argue about or negotiate with our local business owners. You know, that can be a pretty complicated decision of whether or not to put that two-way left turn lane in. And although there's a lot of research and information based on access control and operational benefits of providing some sort of positive separation, we have a hard time sometimes convincing our stakeholders that we really would like to put a median in down the middle of this roadway. Well, the Highway Safety Manual can evaluate this particular picture on the left-hand side. This 4-lane road with a two-way left turn lane, or a 5-lane section, if you will, we can essentially examine it and predict that we should experience approximately 26 crashes for every mile of this roadway per year. What's interesting is if we were considering that median down the middle and taking away that two-way left turn lane, using the Highway Safety Manual, we could evaluate and basically describe what is a substantive safety benefit, not just the operational benefit, but what are the substantive safety benefits of adding this median. And in this case, we're 20,000 ADT in this type of section of roadway. We would expect that by putting that median in, we would be able to reduce crashes down to approximately 4 crashes per mile per year. That is a very powerful message that you can take out to your stakeholders when you're in the design decision-making process. The Highway Safety Manual that AASHTO is publishing, it is, in a sense, it is very similar to the Highway Capacity Manual in that it is a method. It is a system of mathematical equations that can help us assess the safety performance of our roadways and our design decisions. It can help us quantify this performance in terms of giving a numerical answer to what would happen if we did this. And it helps us make informed decisions. And just like the Highway Capacity Manual, it is very helpful to have numerical values and information to demonstrate the trade-offs of different design decisions in terms of safety. The Highway Safety Manual, in a lot of ways, like I said, is like the Highway Capacity Manual in that it describes the mathematical relationships in terms of safety performance based on exposure and roadway conditions and roadway design. It is an analysis tool only, just like the Highway Capacity Manual. It is not a standard. It is not a best practice guide. It is an analysis tool. And also, the Highway Safety Manual will not supersede any other publications, particularly the MUTCD and Green Book, if there's any conflicts that arise with the HSM. I believe in the preface of the Highway Safety Manual, it instructs you to use engineering judgment and to refer back to the previous manuals, either the MUTCD or the AASHTO Green Book, as superseding. So conflicts you would defer to the Green Book and MUTCD. So the Highway Safety Manual is a set of tools, and it is a set of tools that will help you predict crash frequency and also crash severity. And this is how you can now quantify your safety analysis and use some real numbers to help you make decisions. It is also going to be very helpful for you to utilize this throughout the entire project development process, which is a part of the Federal Highway Administration's requirements. We expect that safety will be considered throughout the entire project development process. It is a synthesis of valid highway safety research, and so it is a collection of that research, as well as it provides these tools for predicting the impacts of your decision making. And that's the real value of the Highway Safety Manual. Sorry, I back up here. So it's a collection of the best research and then the best science. A lot of what you'll find in the Highway Safety Manual has not been published in other documents necessarily. A lot of it has been published in other documents. It has certainly been worked over heavily, and it is basically a synthesis of established research that's available for you to use. Now, to put this into context, if you will, the Highway Safety Manual can help you in a lot of ways. And if you look at the project design decision-making process, you are all very familiar with evaluating the impacts in terms of the environmental impacts of your projects. You establish how much acreage of wetlands are you going to impact, and you do it to a very finite level. You know exactly what the impacts will be. In terms of operational analysis, using the Highway Capacity Manual, we can very definitively describe the impacts operationally to our roadway in terms of our design decision-making process. We can evaluate the trade-offs of the costs of our different design decision-making. And all of this are ways we can quantify and evaluate these different decisions we make. Well, the Highway Safety Manual now allows you to develop numbers where you can quantify the safety impact of the different design decision-makings. Design decisions. This helps you make better decisions and more informed decisions related to safety. So how can crash prediction be used? Well, in a number of different ways. At the higher level in your agency, at the program level, you can use the Highway Safety Manual to help you prioritize various segments of roadways or different locations for where you want to apply different treatments or different pots of money in order to affect safety. On a project level, you can assess the relative needs for a specific type of project or different decisions if incorporated into a project. It is also a very powerful tool to help you communicate the relative needs in terms of safety to the public. And go back to that example, the two-way left turn lane. It's a very powerful message that you can take out there about how many crashes you can reduce per year, per mile. And so it's very powerful in that sense. It also helps you prioritize the work that you're dealing with in terms of your project. You can evaluate the cost-effective and the prudent design decisions that you may be looking for. And it also can help you with supporting your design exceptions. If you're dealing with a design exception, the Highway Safety Manual could help you make some of the justification for that design exception. I'm not going to go into tort defense. I mentioned earlier, this is essentially up for each of you to determine how you could possibly use this in terms of tort liability, but there may be some usefulness in terms of tort defense. I'll just leave it at that. Now, I mentioned Federal Highway Administration. It is our policy that safety is considered in every aspect of the project development process. That's including planning all the way through maintenance and operations. And this Highway Safety Manual will certainly help us in all of these areas. When we look at balancing safety, it used to be, before the Highway Safety Manual, that while we could we could quantify the impacts of capacity or the right-of-way costs or the project costs or the environmental impacts, we had numbers that we could associate with the different alternatives, and really those dominated our design decision making. But now we have safety, a quantitative way to evaluate safety, and that can help us balance or bring safety back into the conversation about what design decisions should we be making and what are the impacts of those decisions. In terms of crash prevention, design, with our designs and our project designs, we have the ability to influence the chances or the occurrences of humans making errors in their driving habits. We also have the ability to influence that error resulting in a crash, or if it does result in a crash, what the severity or the consequences of those crashes are. And so we can start to understand, well, what are these different design decisions going to do in terms of preventing or reducing the chances of a human making an error while driving, or the consequences of that if it results in a crash, as far as in terms of severity or even reducing fatalities. So we can understand the engineering, and we can start to look at it in terms of both how it will operate, but also how it will impact the severity of our crashes. And so this is a very powerful tool for you. So what can it do for you? Well, can it predict the safety performance of geometric design features? Absolutely. Can it quantitatively calculate safety effects of your design decisions? Absolutely. Can it predict the safety performance of intersections, or in this case, roadway segments for urban or suburban multi-lane roads? Absolutely. We can do all of this with the Highway Safety Manual. And when we can do this, if we have a tool that will help you do this, we will be making better decisions in terms of safety. And so it's good for our project design decision-making process. So with that, I'll wrap up the introduction. We've talked a little bit about substantive safety versus nominal safety and the performance of suburban and urban streets. And now I'm going to turn the webinar over to Gene Amperano, who's going to cover the prediction of crash frequency and safety performance functions. Gene?
Thank you, George. Just need to get my spot here for a second. This session, what we're going to be doing is we're going to be looking at the prediction models that are used to determine the crash frequency for urban and suburban streets. And when we say prediction models, what we're talking about are the safety performance functions that are used to calculate the predicted crash frequency for a given set of base conditions for an urban suburban street. And we will list those base conditions in a few moments. First, let's define what these particular safety performance functions apply to with respect to urban and suburban roads. The methodology does apply for 2-lane and 4-lane undivided and divided urban and suburban highways. And what is the definition of urban, suburban? Well, it's defined as an area, urbanized areas that include populations of 5,000 persons or more. There are separate prediction models for highway segments, and there's also separate performance models or SPF functions for intersections. The intersections for urban and suburban streets were presented in June 22nd, and copies of those presentations are available at the conclusion of this in the web presentation file share pod. But today we're going to be focusing on highway segments. The definition of a segment, well, a segment can occur anywhere along a roadway, but if it happens to fall between two intersections, then you would want to establish your end and beginning of your roadway segment at the center of each intersection. Also, when you look at your crash data, if you try to compare your existing performance to your proposed or predicted values, then you would have to determine what
crashes are intersection related and what crashes are segment related. And here's a recommendation from the Highway Safety Manual where the physical limits of the intersection are either the limits of the crosswalks or the limits of the curve radii. And those crashes that occur in Area A would be considered crash-related crashes, and crashes that occur in Area B would be considered segment-related crashes. But some states have set specific distances from the center of an intersection to determine whether the intersection or crash is intersection-related or segment-related. For example, some states choose 200 or 250 feet from the center of the intersection to classify a particular crash as either being intersection or segment. But basically what it comes down to is you have to look at the crash report if it's outside the limits of the intersection itself to determine whether or not that particular crash is related to the intersection itself or the segment. Before applying the HSM crash prediction methodology, the roadway itself must be divided into homogeneous units. And those units is based on the bulleted items listed here, such as the average daily traffic or the traffic volume, the number of lanes, whether you have medians present, whether there's parking along the facility, and we're talking about urban roadways and suburban roadways, the presence of fixed objects, the presence of lighting, and also the category of speed. And that could involve either the actual or the posted speeds. So anytime that you have a change in any of these elements or characteristics, then you would want to segmentize or divide that section of roadway into like or homogeneous units. For divided roadway segments, to account for the variability of median widths, a range of widths are given to assign a rounded value. That is used to determine the crash modification factor value for a particular median width. So looking at the chart which came out of the Highway Safety Manual, if you have a median width between 25 and 34 feet, then you would call that, for the sake of analysis purposes, a 30-foot median. The procedures for conducting a crash prediction on a roadway segment is the application of the safety performance models, the crash modification factors, and also you can choose to calibrate your predicted values if you so choose that will bring your predicted value in, make it more reliable for local conditions. So if you have crash data available, you can calibrate the factors so that it represents your geographical area. And in Part C of the appendix of Part C of the Highway Safety Manual, it has a step-by-step process that walks you through the calibration process. But to begin with, you would apply the safety performance function, and this is for urban suburban streets. It has three components, and those three components are listed here. It's the BRMV subscript and the BRSV and the BRDWI, which basically is just multi-vehicle crashes, single vehicle crashes, and driveway-related crashes. We will walk through the step on how to look at those. Now, once you've determined your predicted value for base conditions for the equation above, then you would apply your appropriate crash modification factors that makes adjustments for either your existing or proposed conditions. And then finally, you would factor in your pedestrian and bike collisions, vehicle to pedestrian collisions and bike to vehicle collisions to come up with the total predicted crashes for the particular roadway segment. And this is how they related the circled items. And in this particular session, we're going to be walking you through the process of how to calculate a predicted crash frequency for base conditions. But first, there's 5 types of collisions that are considered. There's multiple vehicle driveway collisions. It's number 1. Number 2 is single vehicle crashes. Number 3 is multiple vehicle driveway related crashes. Then 4th is pedestrian crashes, and also the 5th is for crashes involving bicyclists. And if you look at the far right column, you will see that there's Highway Safety Manual has set up or listed the appropriate equations and figures and tables that are applicable to determine those type of crashes. We're going to cover the first 3 in this particular session: the multiple vehicle non-driveway crashes, single vehicle crashes, and multiple vehicle driveway crashes. The safety performance that calculates predicted crashes for a given set of base conditions is shown here. Again, it has 3 components, which consist of the multiple vehicle crashes per year for base conditions, the crash frequency of single vehicle crashes per year for base conditions, and then the crash frequency of multiple vehicle driveway related crashes per year. What are the base conditions? Well, they're listed here. The base conditions for urban and suburban roadway segments consists of the presence or the lack of presence of on-street parking, roadside fixed objects, whether they're present or not, median widths, if you're dealing with divided segments, and the base condition for a median width on a divided segment is 15 feet. The 4th base condition is lighting, whether it's present or not. Then the 5th one is automated speed enforcement, whether it's present or not. And each of these have a CMF that will be discussed in the next session with Fred. Once you've calculated your safety performance function or your predicted value for base conditions, which is in SPFRS, then you can apply those to your existing conditions by selecting the appropriate crash modification factors that will adjust your predicted value down to what is in the actual roadway itself or what is in the proposed alternative. And finally, you would come up with a total predicted value for your roadway segment would be to add in your predicted crash frequency involving pedestrians and bicyclists. That would come up with your total predicted number of crashes for the roadway segment. And like I said earlier, you can choose to apply a calibration factor that accounts for geographic conditions for your area. And then finally, to sum it up, for the total predicted crashes, you would take the total predicted crashes for your roadway segments and add them to your predicted crashes for the intersections that were analyzed as a part of your roadway unit, if there were any, and come up with a total predicted number of crashes for your entire roadway segment. The safety performance models addresses 5 types of roadway segments. The first one is 2-lane undivided arterials. The second is 3-lane arterials, which includes 2 lanes plus a center 2-way left turn lane. The third is a 4-lane undivided roadway. Fourth is a 4-lane divided roadway, which includes median or depressed median. And then the 5th is a 5-lane arterial, which includes 2 lanes each way with a center 2-way left turn lane. There are some limits to the application of the safety performance functions, and the limits are based on the traffic volumes, and they're listed here for each type of roadway classification. And if your sites that you're analyzing, if the ADTs or the traffic volumes differ substantially from what is listed here, then the further you get away from your outside of these traffic volumes, then the less reliable your results will be. This is a statement that concerns 6 lane units, segments. If you're happening to be analyzing a 6-lane undivided or divided arterial, you can apply the methodology using the coefficients that we're going to show you for 4-lane undivided and 4-lane divided, but they suggest that you do so or that you proceed cautiously. If your ADTs are close to what was given in the upper limits, you should be fine, but if your ADTs are substantially outside of those limits that were presented earlier or in the previous slide, then your results are going to be affected by that. Okay, the first safety performance function we're going to talk about is for multiple vehicle non-driveway crashes, where you have 3 or 4 variables. The first is your traffic volume. The second is your length of your roadway segment in miles. And then you have some A and B regression coefficients that we have to use that come from Table 12.3 out of the Highway Safety Manual. And this is a copy of the Table 12.3 for total crashes. Again, you can see on the far left is the roadway type, where there's a 2-lane, a 3-lane, 4-lane undivided, 5-lane divided, or 5-lane. And then your coefficients would be your A or B coefficients. Again, these are for total crashes. We often get asked, what does the K value mean? Well, it's the over-dispersion parameter that applies to a specific safety performance function. So the K value applies to this particular safety performance function, and it's used if you're interested in applying the empirical Bayes methodology, and that's covered in Appendix C to Chapter C as a step-by-step process. If you're interested in applying empirical Bayes to improve the reliability of your predicted value, you can choose to do that. We don't have time to present that. It's a lengthy process, and it's difficult to explain. This is a picture of the total table of regression coefficients for the safety performance function for multiple vehicle non-driveway crashes. The previous one, we just had the top portion where it showed the regression coefficients for total crashes. But if you wanted to, you could use the coefficient for fatal and injury crashes and use those in the model to come up with a predicted number of fatal and injury crashes only, or you could also do it for property damage crashes as well. Here's an example. We have a 4-lane undivided commercial suburban street. Our traffic volume is 24,000 vehicles per day. Our project length is 3.6 miles. We want to calculate the predicted total crash frequency for a multiple vehicle non-driveway crashes. And so we're going to use the coefficients out of Table 12.3 for the 4U, 4-lane undivided segments. Plugging those A and B coefficients in, which is the minus 1163 and the 1.33, then our 24,000 ADT and our 3.6 miles in length, plugging those into our model and performing the calculation, we come out with predicted crash frequency of 21.4 crashes per year for base conditions. Now, as a comparison, we're going to do the same calculation with the same traffic volumes, the same length, but we're going to use the coefficients for a 4-lane divided. So selecting those coefficients for a 4-lane divided roadway segment, which is the A and B coefficients are the minus 12.34 and B coefficients 136, and then factoring in or putting in our traffic volumes and our project length. what would you expect our crashes to be? Would you expect them to be higher or lower? Well, if you look at the values, and we're going to calculate them here, we find that we went from 21.4 crashes down to 14.3 crashes. That's nearly a 33% reduction in our predicted reduction in crashes. So what we're saying here is that, and this clearly demonstrates, is that a 4-lane divided roadway segment has potential to be 33% safer than a 4-lane undivided. Our second safety performance function that we need to look at is the one that's for single vehicle crashes. It's the same function for multiple vehicle crashes, where we have traffic volume as a variable, the length of our roadway segment as a variable, and then we have, again, A and B regression coefficients we get from a separate table, which is table 12.5. This is a snapshot of table 12.5 out of the Highway Safety Manual. This is for the top part of the table, which deals with total crashes. Again, the K value is an over dispersion parameter for this safety performance function that is used to apply the empirical Bay methods. This is a view of the entire table, where if you wanted to, a person could calculate the expected frequency of fatal and injury crashes using the appropriate A and B coefficients based on the roadway type, and they could also do the same for property damage only crashes. Now we're going to go through an example of calculating single vehicle crashes for a 4-lane undivided commercial suburban street. We're following along with the previous example of 24,000 vehicles per day for our traffic volume. Our project length is 3.6 miles. We're going to use the coefficients, regression coefficients out of table 12.5 for a 4-lane undivided segment. Entering those values, our A coefficient is negative 799, our B coefficient is 0.81, then our ADT and our traffic length of our project, come up with the predicted crashes. For single vehicle crashes, 4.3 crashes per year. So we had, for multiple vehicle crashes, it was 21.4. For single vehicle crashes, it's 4.3. So there's less probability of single vehicle crashes occurring as opposed to multiple vehicle crashes. As a comparison, we're going to do the same calculation, but this time we're going to use the coefficients for 4-lane divided as opposed to a 4-lane undivided. What would you expect to occur? Would you expect 2.6 crashes per year, 4.2 crashes per year, 8.4 crashes per year, or 12.6? Our previous value was 4.3, and going along with what we would expect the 4-lane divided to be safer, so we would expect something less than 4.3 crashes per year. But we will run through the calculations, substituting in our values for a 4-lane divided, getting the regression coefficients from 12.5, come up with a predicted value of 2.6 crashes per year, which is a 40% reduction for single vehicle crashes. Our next and final safety performance function that we're going to present shortly is the one for determining the predicted number of crashes for driveways along an urban and suburban road. But this particular chart here, or slide, is to show that the problems of caused by driveway-related crashes. 72% of driveway-related crashes involve a left-turning vehicle. 28% out of that 72 is a car turning from off the major road onto the minor roads, and those are angle crashes. 34% are minor road traffic turning onto the major road. Again, those are angle crashes, and they represent 34% of the crashes. And then the remaining are from the minor road turning on the major road, which represent either a rear end or a side swipe crashes. Those take about 10% of the crashes. So to determine the predicted crash frequency for multiple vehicle driveway-related crashes, this is the safety performance function that we would use. And it will give you the predicted number of crashes for base conditions. Where little n of j is the number of driveways within the roadway segment for a particular driveway type, and we'll list what those driveway types are. The capital N's of j is the number of driveway-related collisions per year for a driveway of a specific type, and we get that value from table 12.7. T is a coefficient for traffic volume. Again, that comes from table 12.7. Then we have our traffic volume in vehicles per day. So this is table 12.7 where we get our coefficients. It's based on the driveway type, which is the capital N's of j in the left column, and based on whether you have a major commercial driveway, a minor commercial driveway, a major industrial driveway, a minor industrial driveway, or a major residential or minor residential. Major driveways are those that serve sites that have more than 50 or more parking spaces. Minor driveways are sites that have less than 50 parking spaces. And we're going to walk you through an example of using the coefficients for a 4-lane undivided segment. This is where a spreadsheet can come in handy. This example, we're following along with the previous example. We have a traffic volume of 24,000 vehicles per day. Our project length is 3.6 miles. But we have 3 major driveways, or commercial, 42 minor commercial driveways, 2 major industrial driveways, 5 major residential driveways, 2 minor residential driveways, and 7 others. So using the coefficients from table 12.7 for a 4-lane undivided, substituting in our values, this is the calculation that needs to be performed. Again, a spreadsheet comes in very handy. There are spreadsheets available. We can make them available. I think they're in the file share pod, but if they're not, we can certainly put them there. And crunching through all those numbers, we come up with a predicted number of driveway-related crashes of 7.1 crashes per year. This is for an undivided roadway segment. Now we're going to do, as a comparison, the same calculation, but we're going to use the 4-lane divided segment and the coefficients for that type of roadway. So we've had a value of 7.1 crashes per year. What would be the predicted number of crashes would you think would take place if we were to go to a 4-lane divided segment as opposed to a 4-lane undivided? Again, following the occurrences that I have taken, previously, is that the 4-lane divided, in most cases, are safer than the 4-lane undivided. So using those values, we come up with a particular, or the predicted crash frequency of 1.3 crashes per year. That represents an 82% reduction in driveway-related crashes, and it's basically because you're taking away those left turns. To come up with the total predicted number of crashes per year for base conditions, it's just a matter of adding the calculated predictions for your multiple vehicle crashes, your single vehicle crashes, and your driveway-related crashes. And that's what we're showing here, where we had 21.4 crashes per year for multiple vehicle crashes, 4.3 for single vehicle, and 7.1 for our driveway-related crashes. So we come up with a total predicted number of crashes, about 33 crashes per year for this 3.6-mile roadway segment of a 4-lane undivided roadway. The next step is to adjust the predicted value for base conditions to either existing conditions or proposed conditions, and you would do that by applying crash modification factors that adjust your predicted value to reflect actual conditions or proposed conditions. And Fred Rank will be presenting that in the next session. That completes this session where we discuss the safety performance models for predicting crash frequency for an urban street for base conditions. And with that, I will turn it over to Fred.
Thanks, Gene, and I appreciate the opportunity to present to you today. And here's our session on CMFs. For some whatever reason, it wants to start on slide 3, which it tried to do with Gene earlier in his session. In this session, we're going to cover the crash modification factors to adjust the crash frequency we predicted based on the models that Gene presented in the previous session for suburban, urban, multi-lane streets. So we're going to describe the 5 crash modification factors that are available, and then we're going to give you specific examples of how to apply them in the real world to multi-lane suburban urban streets. So the procedure is, first of all, for a roadway segment, we combine all the base models and then the CMFs that we're going to cover in this session and a calibration factor to get our total amount, which are, so first we have our safety performance functions for our segment, which consists of our multiple vehicle crashes, our single vehicle crashes, and our roadway crashes. Then we plug that value into the equation that is shown in slide 3-3 and apply then the CMFs, or crash modification factors, for each of the known 5 effects where the effect is different than the assumed base conditions. And then with our predicted value, adjusted for CMFs, we can then add in the number of predicted bed crashes and bike crashes. The Highway Safety Manual rigorously and comprehensively includes prediction of ped crashes and bike crashes for urban multi-lane segments and for urban multi-lane suburban intersections. Without this, it would have been a big hole in the entire methodology. By being able to predict and include them, we're able to then cover all road users in a comprehensive manner. And hence, it's a holistic approach to predicting crash safety. So our next step is the crash modification factors and adjustments. So our safety performance function, sub RS, is for our segment, our road segment section, and our CMFs are for each of the 5 known factors, and we'll then now describe them to you. For on-street parking, for roadside fixed objects, median width, lighting, and automated speed enforcement. Now you'll notice for urban, suburban, multi-lane, there are no CMFs for lane width, shoulder width, side slope, all of the things that in the rural environment that were major significant effects. Those are not known CMFs in the Highway Safety Manual for urban, suburban streets. Curb parking is the first of the CMFs, and curb parking can consist of either parallel or angle parking. And we have values for the F factor for parking in table 12-19 for each of the 5 models, whether it's the 2-lane urban, 3-lane with a 2-way left turn lane, 4-lane undivided, 4-lane divided, or the 5T model. And each of the parallel and the angle parking has a column for residential or for commercial or industrial institutional. You notice that the biggest effects of parking are, and the biggest factors in this table occur over on 2-lane and for 3T models in commercial industrial settings. The factor for 4-lane undivided and 4-lane divided of 3.999, just about 4.0, is a huge significant factor for the multi-lane urban streets. Now, our P sub PK is the proportion of curb length without parking. And curb length with, with parking, curb length with on-street parking, both sides, is the length in miles. So if we have a 1-mile segment and we take out of the 1-mile segment the length, which is measured center of intersection to center of intersection for our segment, we take out the no parking zones that are provided at the corners of either end for sight distance and for any intermediate intersections within the segment, as well as for fire hydrants and other marked no passing zones, parking zones, we will end up with a length that's less than the measured center to center length for the segment. And I'll give you an example of how to apply that and how it works.
Fred, this is George. Let me interrupt you real quick. I'm getting several messages on the screen that we're having problems, that people can't see the screen.
It's been activated. They should be able to see the screen now. Have the toggle to adjust between full screen.
Okay. Sorry about that.
Okay, hopefully it's better now. The full screen toggle for participants is on, and I double checked it before I go on any further. Let me continue on with slide 7. Gene, if you can, check the adjustment while I continue on with our presentation. For a 4-lane urban commercial street, 4U model, angle parking, which has a more severe effect than parallel parking, one side. And our measured length for parking is 3.12 miles out of the length, center to center of the end-to-end intersections, of 3.6 miles. Plugging in our values for length of parking, which is 3.12 out of our total length of 3.6 miles, one side, shown as a 1, and our factor from the table of 3.999. The calculated value for the CMF is 2.30. This is a huge CMF. The effects of things like a foot of shoulder, a foot of lane in the 2-lane rural environment are 3, 2, 4% at most. When you see a factor that's 2.30 or 230% of the predicted value, that is a major, major significant effect, and will have a huge effect on predicted crashes. Parallel parking, both sides. So we switched from angle parking one side. Now we'll give you an example for parallel parking both sides. Same lengths of the parking zones. We now show a 2 for 2 sides for the length. Our factor is different. It's 1.709 for parallel parking. And the calculated value for the CMF is 1.614. Still 61.4% higher than having no parking, but not nearly as severe as the angle parking on one side, resulting with a fact CMF of 2.30. So parking is a huge, huge factor. And for those of you who deal with projects in which the local businesses and the local city and village in behalf championing retention of parking, you can point out to them the known predicted safety relationship between parking and crashes. The next CMF that we're going to cover is for roadside fixed objects. The CMF is a function of the offset of the fixed objects, their density, and the fixed object proportion of total crashes. Only point objects that are 4 inches or more in diameter, think of trees, and do not have a breakaway design are considered. Point objects that are within 70 feet of each other longitudinally are considered as a single object. So this is not a real precise every tree, every power pole calculation. This is more a functional calculation based on what the average or typical condition for the segment would be. Our fixed object offset factor varies by the width of the offset from 2, 5, 10, 15, 20, 25, and 30 feet in terms of the value of the factor. And our proportion of fixed objects collisions varies from the 2U model of 0.059 all the way up to 0.36 for the 4-lane divided model. For example, a 4-lane urban undivided street, so it's the 4U model with power poles at 2 feet, and 2 feet would give us a fixed object offset factor of 0.232. Our 4U model is a proportion value of 0.037. We use those values and then plug them into the equation for the CMF for the offset value and for the proportion. And we calculate the CMF to be 1.265 or 26.5% higher crash frequency for power poles, one side, 150-foot spacing. And you'll notice that the spacing is a function of 5,280 feet per mile divided by the spacing, which will give us the number of fixed objects, which is our density of the objects. For a 1-mile segment of 4-lane urban undivided commercial curbed, so it's a 4U model with power poles on both sides, 150-foot spacing, 2 feet back a curb. Our density now has changed because we have power poles at 150-foot spacing both sides. And hence, when we double up both sides, we get a more significant effect. More crashes would result from power poles on both sides. As an example, here's a 1-mile segment of urban undivided commercial. 4U model, trees, 12-inch diameter, so they're larger than the 4-inch, and they would be considered as a fixed object. One side, 80 feet apart, 5 feet back a curb. An 80-foot spacing is a fairly typical urban landscape spacing for trees. Trees tend to be spaced out at about half the distance or spacing of urban lighting, and urban lighting tends to be around 150, 160 foot apart. So our trees are at that half spacing for this example. Our values for our offset would be, F offset would be from the 5 foot back of curb from the table, and our density for the 4U model, the 0.037, again, comes from the table for the 4U model. So our value is about 1.288, which is about 28.8% more crashes. The third is median width, and our assumed median width is 15 feet as our base value, and this is without a median barrier. So this applies only to divided roadway segments with traversable medians without a barrier. I do call your attention to the note about the effective traffic barriers on safety would be expected to be a function of the barrier type and offset rather than median width. However, the effects of these factors on safety have not been quantified. Until the HSM is been improved, more information is added to it, we're going to use a CMF value of 1.00 for medians with traffic barriers. Lighting is the fourth item, and lighting has a known pronounced effect in reducing nighttime crashes on urban-suburban segments. We have proportions for injury and for fatal crashes, as well as for the proportion of total crashes for an unlighted roadway segment. Our CMF value is a function of the equation and the coefficients. So for a 4U model, we would take the coefficients for injury and fatals, for property damage only, and for proportion from table 12-23. Remember that lighting is a very effective tool in reducing nighttime crashes. However, most of the traffic and traffic exposure is during daytime hours. So we have less traffic at night that we're affecting with lighting in reducing crashes. Hence, we don't see that huge an effect as you might expect in affecting total crashes. And our CMF values are being applied to total crashes. So an example, we have power poles, 150-foot spacing, 2 feet back a curb, and we're going to add lighting. So our lighting for our factor would be, adding in our factors from the table, 0.917, or about 8.3% reduction in crashes overall of total crashes, but a much more bigger effect of nighttime crashes. However, lighting, well, it adds light poles at the 160-foot spacing on one side, set back 2 feet from the back of curb. So we're going to need to recompute our fixed object CMF. So for our 1 mile segment, 4U model, power poles one side, 2 feet back of curb, street lighting on the other side, 160-foot spacing, 2 feet back of curb. We will do the calculations within the offsets. We have the same offset, but we have to add in for the pole density. And so we have the 150-foot spacing to give us the density for the power poles, and 160-foot spacing on the other side for the lighting poles. Our 0.037 is for our 4U model, and our value is, adding the two together, is about 1.548, or 54.8% more crashes than if we had no lighting poles and no power poles. So as you can easily see, the effects of parking are huge and significant. The effects of roadside fixed objects are huge and significant. And when you add in lighting poles and trees in the suburban urban environment, you may expect the predicted crash frequency to be significantly increased. So as a further example and a short exercise, let's look at a 1 mile segment of 4-lane urban. So it's a 4U model, undivided. If it was divided, it'd be the 4D model, with trees. It's commercial curb street trees, 12-inch in diameters, 80 feet apart, 5 foot back of curb, both sides. Street lighting, 160-foot spacing, 5 foot back of curb. And this would be a fairly typical suburban, urban cross-section that has aesthetic treatments of trees and lighting. So we would calculate our fixed object crash modification factor to begin with from the trees and from the lighting for our density of fixed objects, and we get a fairly high effect, and CMF of 1.937 almost doubles the resulting crash frequency. This is a huge effect. Now the effect of changing those luminaires to breakaway takes out the portion that's the lighting and would reduce our CMF accordingly. And we end up with a lower value of 1.613, only 61.3% more increased crash frequency. And that's from the trees. Our fifth CMF for urban suburban streets is automated speed enforcement. You can now apply all of these together into the total result. And this is the power of the Highway Safety Manual, is that we can take the effects of individual measures and combine them mathematically by multiplying the effect of one to the other with these known CMFs that come from the 3 chapters in Part C of the Highway Safety Manual. So our effect of commercial on-street parallel parking of 1.613, roadside fixed objects when non-breakaway light poles, 1.937, lighting slightly decreases by 8.3% our predicted crash frequency. Our median is the nominal assumed base condition, and there's no speed enforcement. So our total effect on the section that Gene provided to you in the previous session 02 for the 4-lane urban at 24,000 ADT, 3.6 miles long with the driveways, it resulted in 32.8 crashes. And when we have applied the effects of trees, lighting, parking, we end up with 93.9 crashes per year. These are big effects. So the further back from the edge of the travel lane that you can place trees and light poles, the more that you mitigate parking to be parallel and to restrict its amount of parking on the total length of the street, the more you reduce crashes in urban suburban sections. This is a good working example that we've provided to you. We've covered in this session the crash modification factors, the 5, from urban, suburban, multi-lane streets, and we've given you examples, provided them for how to apply those CMFs. Now, interestingly enough, and let me say it again, is that there, in the Highway Safety Manual, there are no CMFs to adjust for lane width or shoulder width, and for urban, suburban streets, nor for side slope, or for some of the other effects that we've seen out there. At this point, I know that Gene and Apparano and George Merritt have done a real active job in providing answers to you in the chat pod to the questions that are proposed in the chat pod. I would ask our operator, Holly, if she would be so kind to open up the lines, and if you have a question, you may certainly pose it now to us to answer.
Thank you, sir. At this time, if you would like to ask a question, please press *1 on your touch-tone phone. Please record your name clearly. Your name is needed to introduce your question. To withdraw your request, you may press *2. Once again, please unmute your phone and press *1. Record your name so I may announce you. One moment for the first question. First question I'm showing comes from Dan Thompson. Your line is open.
Yes, I do notice we had the adjustments for pedestrians and bicycle crashes that we didn't fully discuss, but what effects do bike lanes have on crashes?
It's a very good question. First of all, to predict bike and ped crashes, we didn't cover it today, although it is there. It's extensively covered in Chapter 12 of the HSM. And thank you for the lead-in. On Monday, we will be doing a webinar starting at 11 a.m. Eastern Time to present to you the technology, the known safety effects from the Highway Safety Manual for the prediction of pedestrian and bicycle crashes to urban, suburban, multi-lane segments and intersections. And the material is extensive enough that it'll take us 2 hours to present just that for bikes and peds. Now, the second part of the issue that you described is, what's the effect of the bike lane? Well, the bike lane is moved further away from the edge of the travel way, and hence it increases the offset distance to any fixed objects such as trees or light poles. If parking is provided, a parking lane increases the offset for the fixed objects back further, and hence we see less of an effect.
Good point.
Are you ready for the next question?
I'm ready.
Okay, thank you. And once again, if you do have a question, please press *1. Amanda Watson, your line is open.
Hello, yes. My question was regarding the automated speed enforcement. What does this conclude?
It's automated speed enforcement rather than by just policemen. It would be a automated system that can essentially ticket every vehicle that passes it, give it a citation if the speed is above a threshold at which enforcement is allowed in the court in that area. And this is not the traditional enforcement for speed, nor is this a CMF that for speed tolerance or for speeding or speeding above the posted limit. It is purely do we have the presence of automated speed enforcement, which has been known and is published in the Highway Safety Manual to directly affect driver behavior.
I'm showing no further questions.
Okay, no further questions. I know that Gene Apparano and George Merritt have done a really good job in the chat pod, and I'm going back over the chat pod questions now, and just to see if there are ones that we did not cover and provide answers back out to you in total. And Gene or George, you can certainly jump in and start any time in answering anything that we haven't covered in the chat pod.
Okay, what does BR means in BR of the safety performance models? It's just what the researchers selected. It's the predicted average crash frequency of individual roadway segments. That excludes pedestrians and bike collisions. I'm sure it probably had some meaning at one time, but it probably lost that meaning through the changed versions of the draft Highway Safety Manual into the final Highway Safety Manual, but they just chose to leave that in there.
There was a question from M. Ali, and let's see if I can go back and find it. A bridge pier in the median can be considered a fixed object. The answer is yes, but the Highway Safety Manual in Chapter 12 does not consider in the CMF value any fixed objects in the median. It is only for fixed objects to the right of the right lane of the roadway. There was a question.
We have a question from Chicago Department of Transportation asking about breakaway poles, whether they're accounted for in the calculations. Any breakaway devices are considered to have a CMF of 1.0, so basically what it's saying, it has no effect.
And Gene and I and others who are involved in the Highway Safety Manual have discussed this at quite length. It's still a crash when you hit it. It's just that they're almost always property damage only and no injuries or fatals occur when striking a device with a breakaway coupling at the base of it. However, it's still a crash. But it's why we call your attention to it in how the Highway Safety Manual methodology works. They essentially are taking them out of consideration and applying the CMF for fixed objects. I'll try and answer the question here from M. Ali. For suburban arterials with on-ramps can be considered as driveways, or do they need to be evaluated as intersections? The key to this is if it functions like a driveway, treat it as a driveway. If it acts as an intersection with full access, treat it as an intersection. This becomes really crucial in sections that are 4U or 4D, because implicit in the 4D model, the divided model, is that all driveways are converted to right in and right out, and you do no longer have full access. So a ramp or that still has full access would be treated as an intersection, and that would be the appropriate way to model it.
We do have a question. Joyce Williams, your line is open.
Hi, I was wondering, as far as if you're doing a project and you've got, homogeneous segments and then intersections, would you end up adding up all of your crash prediction factors for the intersections plus the segment?
The answer is yes, but you're not adding the crash modification factors. You would actually be adding up the predicted number of crashes after you've applied the CMFs for each segment and for each intersection.
Okay. Thank you.
Let's see if I can get back to where we were in questions in the chat pod. We addressed the question from Bonnie Poland, comparing 4-lane to 4-lane divided, excludes the intersections at either end, and the answer is yes. You would assign functionally the crashes with the intersection to the intersection and the segment-related crashes to the segment. Going down through the questions. From Virginia DOT, does the driveway analysis for 4D segments always assume no median breaks? And the answer is yes. Median break for a driveway, then you would convert it over to an intersection if it has full access. Question from Amanda Watson, can you tell me whether vehicle-activated speed reader boards are considered automated speed enforcement? And the answer is yes. From Joe Santos, Florida DOT, how are the directional medians applied in the analysis? If it provides full access, treat it as an intersection. Directional medians are not really covered explicitly in the Highway Safety Manual, but there is an excellent NCHRP report on U-turn median openings that could help you with the values that would be appropriate to adjust for that effect. Question from James Gladys. Does angle parking refer only to head-in and not back-end parking? And the answer is yes at this point in time. As far as we're aware of here at FHWA, I'm not aware of any study yet that's robust enough on back-end angle parking that would warrant a designation for the CMF value. I think what it's going to take is a couple of more years of data, time to go by, and a comprehensive, robust study to be done. Those cities, the major cities such as Seattle that are installing back-end angle parking in a large way will make it excellent locations to study this effect. From N. Palmer, does parking length take into account driveway gaps or not? And the answer is yes. You have to actually measure the length of the parking that's provided. From Gill of New York DOT, is there a CMF for business districts versus residential? And the answer is yes, within the parking CMF only, not for overall for crash prediction or for the other CMF values. From N. Palmer, are signposts considered fixed objects? No, because for the most part, they're less than 4 inches in diameter, and for the most part, they had better be breakaway, crash-worthy, as that's a standard requirement of the National MUTCD. There shouldn't be any fixed object signposts out on the roadway, urban, suburban, or rural. Is there a CMF for school zones for Maryland SHA? And the answer is not yet. The HSM's a very robust first edition of the Highway Safety Manual. It certainly has a lot of good information, well synthesized and put together. But at this point in time, it remains a work in progress, and a lot of the things that we would like to know more about are not yet specifically included in the HSM. In response to Tim Harmon from New Hampshire DOT, wouldn't the difference in driveway types help differentiate between business districts and residential areas? It could, but that's not an explicit consideration in how to apply the crash prediction frequency model nor the CMFs for urban multi-lane streets. From Aaron McVicker, are there different factors for different types of driveways? And the answer at this point is no, it's explicitly covered by the type of driveway rather than the type of development district within the driveway prediction, crash frequency prediction model that Gene covered in session 02. Virginia DOT, the CMFs for roadside objects seem very high, considering there are very few proportion of crashes involving run-off-the-road vehicles. Well, I understand your point, but the research on major amounts of mileage of urban-suburban streets states otherwise, and that actual crash experience for suburban-urban multi-lane is what has produced these CMFs that give us these high values. For Dennis Eden, question, are adjustments for any right turn decel lanes at driveways? Not specifically for that geometric feature for a decel lane. Neither are there ones available for acel lanes. Mark Roger from Illinois DOT. Why are the breakaway items such as light poles have zero effect on crash CMFs? The driver's still hitting the pole and it's still an effect in a crash. Mark, Gene and I and George agree with you. But at this point in time, the context of the Highway Safety Manual on roadside objects is to take out those devices that are breakaway, that are within the clear zone, and they're not considered. But we've always bring it up to make sure people understand that. We wish we knew more about how that got into the Highway Safety Manual, but at this point in time, that's all we can provide to you in terms of information. How about posted speed limit on crashes from Fadi Nasser? There is no CMF of posted speed limit. Speeding and these issues involved with speeding are pervasive across the entire United States. In the analysis of all of the crashes and all of these huge databases from which the Highway Safety Manual is developed, they could not ascertain a linkage, a correlation of speed by itself. And hence, it's incorporated, it's implicit in all of the equations in the CMS, but there's no specific CMF. Michigan DOT, how are driveways with small numbers of parking spaces but a high volume of vehicle turnover treated? Just exactly the way it shows in the Highway Safety Manual. If they have 50 or more parking spaces, they're a major business, commercial. If they're less than 50, they're minor. And that was how they developed the specific CMFs that you find in the Highway Safety Manual. From Neil Schaefer, Baton Rouge, is there a rural multi-lane intersection session on the 13th that wasn't listed? And the answer is why. Yes, there is. And that's the one that we've added in. If so, what's the time? And Gene, could you give them the time? Because I don't have it in front of me.
Yeah, the rural multi-lane intersection is on June 13th, 1:30 to 3:30 p.m. Eastern Time.
I believe Gene's answered it several times in the chat pod, but the question from David Glabus of Oklahoma DOT, is there any software available to do these calculations for system-wide calculations? And the answer is it's safety analyst statewide, and I know that Oklahoma DOT is considering safety analysts to analyze their crashes on their system of highways. Specifically for a project and applying the Highway Safety Manual, in the file share pod that Gene and I will post at the end of this session are spreadsheets that will automate the calculations for you for an individual segment or intersection. Vermont, DOT, can we download this presentation in a PDF? And the answer is yes. That's the format that it will be in the file share pod that we'll put up here as we end this session. From Jennifer Devon, can the urban-suburban methodology be used on streets that are one-way pairs? Yes. They're in terms of ADT, which is total daily volume. You can use it either for a two-way or a one-way street, and it'll work effectively to meet your needs. From Gil, from New York DOT, is there a target release date for the next HSM? And Gene and I are aware that they are working on a second edition. There's a person already who's heading up that effort, and they're collecting information already about gaps and things that need research. So in order for the research to be prioritized to go into the next edition. Now, when that next edition will occur, I'm not sure. Well, I'm not aware of any date, but they're already working on it, and this is at the national level for prioritized research conducted by TRB and CHRP. From the BC Ministry of Transportation, how are commercial establishments that have drive-thrus handled? So they may have less than 50 spaces and would be considered minor. They're handled as minor if they have less than 50 spaces. The Highway Safety Manual Committee truly wished to keep all of the input data as simple as they could. So they did the classification of driveways in terms of parking spaces and traffic exposure on the street in terms of ADT, AADT, or daily vehicular volume in the simplest way it could be handled in order for DOTs and other agencies that may only have the barest minimum of information to still be able to use the Highway Safety Manual. From Brian Arcade, where can we register for the July 13th webinar? You do not need to register per se, except Gene, are you going to put it up somewhere so they can, so there's an available line?
I will send, I'll put down the NHI website. And if you go to the NHI website and look at the NHI calendar, and you go to July 13th, you'll see that particular course listed there. Just click on it, and it will take you to a registration room where you can register for the course. And I'll put that up on the NHI website here shortly. I'm putting it in right now.
Are there other questions that anyone would like to pose either by telephone or in the chat pod?
Once again, *1 if you do have a question on the phone line.
And in response to Jim Jeffrey's question, yes, there is an HSM webinar on the 14th on applications to horizontal curves. With that, operator, unless there's another question, we're ready to end today's webinar.
Okay, I am showing no further questions. This does conclude the conference call. You may disconnect at this time. Have a great day. Speakers, just one moment.